We are now going to take a look at endothermic and exothermic reactions. In Chem 2A, this information is found in Chapter 7, Section 7.9. Notice as an introduction that almost every chemical reaction involves either the gain or loss of energy. And we exploit that, we take advantage of that fact to do chemical reactions like combustion reactions, which release energy, to do work for us like power our automobiles. Right, so given the fact that chemical reactions involve either a gain or loss of energy, we can refer to that concept as heat of reaction and symbolize it with a delta H. And notice the qualification here, it really doesn't pertain much to this class, but would if you went on into more advanced chemistry. That specifically the delta H, or heat of reaction value, applies to reactions done at constant pressure, say open to the atmosphere, which is usually what we're doing when we're doing a reaction. Again, a minor point that really doesn't have a lot of application in a Chem 2A class. Okay, we can take a look at one of two options involving reactions. We either see that the reaction is an exothermic reaction, which means that energy is released or given off by the reaction as it occurs. Notice that if that's the case, if it's an exothermic reaction, that energy would be produced as a, quote, product or along with the chemical substances that are products of the reaction. In other words, energy appears on the right side of the equation as another product, and its value would have a negative number assigned to it. So for exothermic reactions, we can in general say they're going to have this format. The reactants, as they move towards products, will release energy as well into their surroundings. So to understand that, we have to recognize that the reactants have to be starting out at a higher energy state than the products. And remember, we discussed that molecules possess potential energy due to the bonding structure they have, the position of electrons relative to nuclei. So if the reactants are at a higher energy state, they are less stable than the products that they produce in an exothermic reaction. So the products are at a lower energy state than the reactants are, and as you move forward, as time progresses, you're moving to a more stable, lower energy product, and the difference in energy between the reactant state and the product state is released as energy into the surroundings, into the environment. So the delta H value would have a negative number to it. An example is a reaction between hydrogen gas and chlorine gas to form hydrogen chloride. Right? Notice that this reaction is an exothermic reaction. It's releasing 185 kilojoules of heat for every 1 mole of hydrogen and 2 moles of chlorine that react. This is our heat of reaction. This is our delta H. And notice, because energy is being released, given off as the reaction proceeds, we're going to put a negative value with that delta H number. And that number is coming, if you had a numerical scale here for potential energy, it's coming from the difference between the energy contents of the reactants and the products. So the numbers that would be on here, the difference between them would correlate to 185 kilojoules. This just showing a general diagram, not trying to give specific values, but just general. So our heat of reaction, our delta H, a negative 185 kilojoules, and whenever you see that negative number, you know that you are looking at an exothermic reaction, a negative value for delta H. So 185 kilojoules of energy is released into the surroundings when 1 mole of hydrogen reacts with 1 mole of chlorine to form 2 moles of hydrogen chloride. Let's take a look at the other possibility where the reaction is an endothermic reaction. And of course, the prefix endo referring to in or into, exo referring to out or outer. So an endothermic reaction, therm referring to heat, heat would be absorbed or coming in from the surroundings, from the environment as the reaction proceeds. So general format, this energy value would now be on the reactant side. You would need to have energy being absorbed by the reactants in order to form the products. This must mean that on a potential energy graph with potential energy on the y-axis and time on the x-axis, the products are at a higher energy state than the reactants are. Energy needs to be absorbed to move to that higher energy product state. So this difference in the potential energy of the reactants and the products correlates to delta H, the heat of reaction, the heat or energy that's gained by the reaction, and it is a positive value, a positive number. So endothermic reactions, the delta H values have a positive sign associated with them, and this is telling you that the products are at a higher energy state than the reactants. You had to gain energy as the reaction proceeded to move to the higher energy state. An example would be the reaction between nitrogen gas and oxygen gas to form nitrogen monoxide. We see here that energy is showing on the reactant side, meaning that nitrogen and oxygen have to absorb energy in order for this reaction to proceed to form nitrogen monoxide. The nitrogen monoxide is at a higher energy state, therefore less stable, its bonding arrangement less stable than the bonding arrangement found in either nitrogen diatomic elemental or diatomic oxygen elemental. Right, so our delta H value of 180 kilojoules would have a positive sign with it, indicating that this reaction is an endothermic reaction, that 180 kilojoules of energy have to be absorbed from the surroundings when 1 mole of nitrogen reacts with 1 mole of oxygen to form 2 moles of nitrogen monoxide.